So I think you guys already have a pretty good idea that Gauss's law is pretty darn simple. I mean, in not only in concept, but actually in execution as well. As a matter of fact, we make it simple because we don't use it when it won't help us. We don't use it when it's not simple. So we're going to try to make it simple. So, just as a reminder, we're looking at for E.dA. I switched to small a there. It doesn't make any difference. Let's see. Okay. All right. Why am I bringing this up? What's the point? So you already have seen a few videos of somebody else approaching these problems. I don't know if any of you followed up and looked at some more videos that that same guy has. He made a video that's similar to the one that I'm about to do. However, he made a couple mistakes in there, and so I didn't want to give you that one. But I am going to show you another situation in which you can apply Gauss's law. Oh, shoot. There is a section in your book. Hang on just a second. I'm going to pull it up. There's a section in your book that's relevant for this, and that is, okay. In after example 22-8, after that example, there's a discussion of a couple paragraphs long, maybe one long paragraph. I recommend that you take a look at that and make certain you understand what that issue is there. It's not a big deal, but it's something that is kind of important. But the reason I'm bringing it up now is because I'm going to address a problem with surface charge in it, but I'm going to define surface charge in such a way to make it as simple as possible. Not always true. And so, in other words, you can't always define surface charge in this fashion. The way that I'm going to define surface charge is looking at this particular problem that we're looking at. I'm going to look at this charged sheet. So this is a conductor. It's a conductor, and it is infinitesimally small. So its thickness is as close to zero as you can get, but big enough that it can have charge on it. So it's going to have charge Q over its whole area. So this is a sheet that goes in in 2 dimensions. And what's the point? Okay. So, and we're just going to define the charge density. Sigma is equal to the charge per unit area. So it equals charge per unit area, but there's no different charge density on this side than there is on this side. It's just a uniformly charged thin plate with a charge sigma. Okay, the question is, how can we use Gauss's law to help us with this? Well, once again, we have to consider the symmetry here. So we'll go ahead and we'll say that this is in Z and that this is in X and Y here. And we'll go ahead and draw this surface. We'll draw, matter of fact, I'm going to draw it up here. We're going to draw this surface right here. And this is, as I mentioned at the beginning, this is something that's called a Gaussian pillbox. And the reason we're doing this, by the way, is because Gauss's law is very simple. There's nothing more to it than E.dA equals Q enclosed over epsilon 0. That's it. The trick with Gauss's law is just seeing applications. The applications are different. So now everything else that we're going to do is just taking a look at applications. So here's an infinite charge sheet with charge sigma on it. Sigma could be positive or negative, we don't care. But looking at the symmetry of this problem, we know that if there's some part here that is going to put in a contribution of the electric field in that direction, there's some part here which is going to put in a contribution in that direction. The vertical components are going to cancel out. The only thing we're going to be left with is a component that is normal to the surface. So we know that this is our little pillbox. It's a little cylinder that's squat and short, and we know that the sides are going to have no contribution at all because E.dA, the angle there is always going to be 90 degrees. And so there's going to be no contribution. So what is the contribution? Well, let's look at this once again and look at symmetry. is there any reason for this spot, the field at this spot, to be any different than the field at that spot or the field at that spot? No. So we know this field is going to be uniform as we move in x and y. So if the field is uniform as we move in x and y, then all we need to do, concern ourselves about then, is what about this dA? Does the dot dA change as we move about this surface? Well, we are constructing this surface to take advantage of the symmetry, which means we are making these surfaces parallel to the surface, the charged surface itself. Therefore, what we have is, we know that this area here, I'm just going to write it as A. Well, I will take it one other step just to be really explicit. The E we know is in this direction. The dA, we just defined it to be parallel to this surface, which means the dA is also in that direction. So the cosine theta is equal to 1 at all times over that space. So the E is uniform. The cosine theta is uniform. The dA is just a unit area there, which does not vary. And therefore, we can take all this stuff out of the integral, and we just know this closed loop integral here is just going to be EA. But we have an EA for this surface right here. We also have an EA for this surface right here. So what we know for this closed loop, for this closed surface, we know that the surface is 2EA. This is what this E dot dA is going to... Oops, sorry. E dot dA is going to be called a 2EA, which is not 2 each, but 2E times A. And what do we know? We know Gauss's law tells us this is Q enclosed over epsilon 0. Well, what is the Q enclosed? Let's look at this definition right here of sigma. So the Q enclosed for any given area is just sigma times that area, which will be Q times area divided by area. That's just by definition. So our Q enclosed is just sigma A. Okay, so we have sigma A over epsilon 0 equals 2EA. All right. Okay, so this now gives us the electric field of an infinite charge plane with a charge sigma. And once again, we look at this, we define this as Z. If this is plus in this direction, it will be in the... sorry, we didn't actually finish this. Let's finish this. I just realized. Sorry. So what is our E? E is equal to sigma, our A's are going to cancel, over 2 epsilon 0. Okay? And the question is, what is the direction of that? Well, if it's in the Z hat direction just by symmetry. So it's either, if sigma's positive, well, yeah. If sigma's positive, then for positive Z, it will be positive and going in this direction. And if sigma is positive in the negative direction, it'll be negative going in this direction. So it is going to be in the Z hat direction. And once again, if sigma is negative, then it will just be this way and this way. Okay? So now we know the electric field due to an infinite sheet of charge. We are now going to take this knowledge and extend it to other situations in just a minute.